Light is a traveling wave. Light is made up of oscillating electric and magnetic fields. So that's why we spent all this time thinking about oscillations and traveling waves. Light is an oscillating traveling wave. So here we have an example of what a wave of light looks like. We've got the electric field oscillating sinusoidally. Let's say it's oscillating in the vertical direction. And then we have the magnetic field. The magnetic field oscillates perpendicular to the electric field. Okay, this is always the case. The electric field and the magnetic field will be perpendicular to each other. So when we map sometimes the waveform of light, we're really tracking the electric field component. The magnetic field component is perpendicular to that. Well, this is why light is sometimes called the electromagnetic spectrum, because light is the product of electric and magnetic fields oscillating together exactly like this. And maybe it's kind of weird and bizarre, but you have to have these oscillating electric and magnetic fields in order to have light. That's what light is. And sometimes you'll hear the word electromagnetic spectrum. That's because light comes in a variety of forms. Some we can see with our eyes and some we cannot. So electromagnetic waves include visible light, that's what we can see with our eyes, radio waves, which are very, very, very long wavelength waves. That's the waves that travel through the air for Wi-Fi, cell phones, all that kind of stuff, okay? And we have microwaves, literally there's microwaves that are exciting the water molecules inside the food that you heat up in the microwave. We've got ultraviolet light, that's a light in the electromagnetic spectrum that has a wavelength that's just a little bit too short for our eyes to see. Infrared, that's light that has a wavelength that's just a little bit too long for us to see. X-rays, those are part of the electromagnetic spectrum too. Now, all electromagnetic waves travel through a vacuum, or generally like air in the room around us, at the same speed, which we abbreviate as the speed of light in a vacuum as the letter c, lowercase letter c, and that equals 3 times 10 to the 8 meters per second. Okay, that's a very important number for you to remember, and I'm going to expect you to remember the speed of light is 3 times 10 to the 8 meters per second. That's the speed of light in a vacuum, okay? So here we have the electromagnetic spectrum. On the top, we've got the frequency of the wave, and on the bottom, we have the wavelength of the wave. And so we'll note a particular relationship that as the frequency of the wave increases, the wavelength of the wave decreases. So you have a shorter wavelength wave has a higher frequency. A longer wavelength wave has a lower frequency. Okay, so that's what this is saying here. The frequency increases, the wavelength decreases. They're inversely proportional to each other. So for example, if we think about radio waves have a very long wavelength, but they have a very short frequency, okay? All the way over on the other side, when we think about X-rays have a very short wavelength, small wavelength, but they have a really large, really high frequency, okay? So frequency and wavelength are inversely proportional. And the visible wavelength of light are down here, wavelengths of 700 nanometers to 400 nanometers. A nanometer is what we use to represent wavelengths of light pretty close to the visible wavelength. 1 nanometer is 10 to the minus 9 meters. Red colors of light are around 700 nanometers, and blue wavelengths of light are around 400 nanometers. So when we think about light in the visible spectrum, okay, 400 nanometer wavelength of light is like a purple violet color. That is a shorter wavelength that's going to have a higher frequency than the red colors down on the other end of the electromagnetic spectrum, which have a longer wavelength, and they're going to have a shorter frequency or smaller frequency. So I briefly mentioned before that waves carry information. These traveling waves carry information they also carry energy. The energy in a wave propagates, moves in the direction that the wave is traveling, but the components of the wave don't. We already talked about that. Think about the little duck on a pond, and when that wave passes across the surface of the pond, the duck moves up and down. It doesn't move forward with the wave. Okay, so the amount of energy in a wave is proportional to the amplitude of the wave squared. So the energy of the wave proportional to, that's this little sideways symbol, a squared, proportional to the amplitude of the wave squared. Okay, waves can spread out, and not just can, they do spread out as they get further away from the source that created the wave. And this changes the area waves cover, and that has important effects on the intensity of the wave. So the intensity of the wave, when you're thinking about sound, is like, you know, the loudness, perceived loudness of that sound. Okay, for light, the intensity is like how bright essentially does it appear, and that brightness or the loudness diminishes as you get further away from the source. Why is that? That's because that the intensity of the wave is equal to the power of the wave. The power of the wave is dependent on like the source that emitted the wave. Okay, so the power of the wave doesn't change, but the intensity is equal to the power divided by the area that that wave is covering. So that area we can think about as being a surface area, the surface area of a sphere at some distance away from the source. So that surface area of the sphere gets bigger as you get further away from the source. So that's why the intensity of a light source diminishes as you get further away. The loudness of a sound source diminishes as you get further away. Okay. So, and the power here is the power carried by the wave through some area. And a wave's intensity is also proportional to its amplitude squared. The energy is proportional to the amplitude squared. The intensity is proportional to the amplitude squared. So I know that there's some different types of A's floating around in here. At some point in physics, it's important to keep track of what do these symbols represent. Sometimes it's the same symbol, but it will mean a different thing in a different equation. So that's why it's important to understand what's going on in the equations versus trying to memorize what are these equations, okay? In any case, that's something that we'll have to keep track of. The intensity of a wave is inversely proportional to the area through which that wave is being carried. Okay, so that surface area is 4 pi r squared. So that means that the intensity is equal to the power over 4 pi r squared. So the intensity is inversely proportional to the radius squared, the distance away from a source that you are. Okay, and so if you're trying to hear a sound, or you're viewing something from 3 meters away from the source as opposed to 1 meter away from the source, the intensity of that light is going to be, 1 over 3 squared, or 1/9 the intensity that it was at 1 meter squared, because that intensity is inversely proportional to the distance that you are away from an object squared. Energy proportional to the amplitude of the wave squared. All right, so energy here is the capital E, but here we're looking at our light wave. Remember, we said that the light wave is electromagnetic waves, the electric field being perpendicular to the magnetic field, and they oscillate. Okay, so here we have a wave, electric field perpendicular to the magnetic field, oscillating. Here, the amplitude of the electric field, therefore the amplitude of the magnetic field, has been increased by a factor of 2. So if the amplitude is increased by a factor of 2, that means that the energy of the wave is increased by 2 squared, or increased by 4 times. Energy and frequency are also directly proportional to each other when we're thinking about light. So The higher the frequency of your light, the higher energy that light carries, okay? That part of the electromagnetic spectrum carries. Now, energy and wavelength are inversely proportional to each other. I should have said inversely instead of indirectly here. So if your wave has a really high energy, it's going to have a shorter wavelength. If your wave has a lower energy, it's going to have a longer wavelength, okay? And frequency and wavelength are inversely proportional. We already talked about that too. If you have high frequency, you're going to have short wavelength. If you have long wavelength, you're going to have a smaller frequency. For example, an X-ray. X-ray, part of the electromagnetic spectrum, has a very high energy, okay? That wave carries a lot of energy. It has a high frequency. It has a short wavelength. If we go down to the other end of the electromagnetic spectrum, we think about microwaves or radio waves. Those waves have a lower energy, okay? Because they have a lower energy, they have a lower frequency, they also have a longer wavelength. We already talked about the intensity of a wave being inversely proportional to the distance away from the source squared. Now, intensity has units of watts per meter squared. So intensity is a power over an area. So power has units of watts, and area has units of length squared. So that's why intensity has units of watts per meter squared, okay? So we can think about, let's imagine something that's a light source. So a light bulb, okay? Here's our light bulb. Or in astronomy, we think about this as a star, okay? So that light bulb or that star has a power output, okay? That is a constant of that object. And that light has to propagate outward from the source. So as that light moves outward, as we get 1 meter away from the light source, or 2 meters, or 4 meters, or 9 meters away from the light source, the area that that light has to go through increases. And that area that that light goes through is a surface area of a sphere. That sphere is centered on that light source. So the surface area of a sphere is 4 pi r squared, okay? So if we've got power over area, the intensity is proportional to 1 over the area. So it's proportional to 1 over the distance squared that you are away from the source. R in this case is the radius of your sphere, or the distance you are away from that source. So if you're at a distance of 4 meters away from the light source, your intensity has decreased by 1 over 4 squared, or a 1/16 actually of the intensity you have when you're only a meter away from the source. Okay, so that's how that works. Now, the power we saw from last semester, you can also write as the energy per unit time being output by the source. So you can rearrange these in different ways. Intensity is power over area. It's equal to energy over time divided by 4 pi r squared. You could swap these different parts out depending on what you're given in a particular problem. Think about intensity, energy, power, time, distance away from a source, and relate them all with this relationship right here. Okay, so we're going to use this idea of intensity, power, area to think about the intensity from sunlight that we receive here at the Earth. So what is the average intensity of sunlight above the Earth's atmosphere? Okay, what information do we need to solve this problem? I'll let you think about that for a second while I bring up my whiteboard here. Then when we think about the intensity of the wave, all right, we said intensity is equal to power over area. And so we want to find out, okay, what is the average intensity of sunlight above the Earth's atmosphere? What things do we need to solve this problem? Well, we need to know something about power, right? So power equals question mark. We don't know. Well, that wasn't given in the problem. What else do we need? Well, let's see. Area. Maybe we need to know. So this area for our light source, this area is the area through which that power emitted by the source has to go through. And we think about that light as emitting in all directions outward. So that light is going to go through a surface area, the surface area of a sphere. So that area is 4 pi r squared. So we need to know something about r. R would be the distance between us and the sun. So those pieces of information that we need to know. So the power emitted by the sun is 4 times 10 to the 26 watts, okay? And in astronomy, we call this the luminosity of a star, okay? And then the distance that the Earth is away from us, we call that 1 astronomical unit. The astronomical unit is the distance between the sun and the Earth. That's how it's defined. And that number is 1.5 times 10 to the 11 meters. Okay, so with that information, we can figure out the intensity of sunlight above the Earth's atmosphere. We needed the power of the source, and we needed the area that that source is going to be emitting through, which at our location is going to be a surface area of a sphere at a distance of r. Okay, so this power was the luminosity of our sun, 4 times 10 to the 26 watts. And then we're going to divide that by the surface area through which that light is going through, 4 pi and then r squared. Our distance is 1.5 times 10 to the 11 meters squared. So our answer is going to be 1,400 watts per meter squared. So remember, the unit of intensity is watts per meter squared. So that is our average intensity of sunlight above the Earth's surface. You're going to be asked a similar question in your workbook where we think about the intensity of light from a star on a planet, some distant solar system. And in that case, you're also going to be thinking about intensity is equal to power over area, but you're going to want to use the alternate form, or we can say that power is also the same thing as energy over time. And so you're going to use that relationship in one of your workbook problems whenever you encounter it. Okay, so just keep that in mind. So now we're going to test, have you been paying attention? Well, we have two identical waves, and they each have an intensity of 1 watt per meter squared. So the first question I'm going to ask is, what is the amplitude of the resulting wave? Okay, what is the amplitude of the resulting wave from this perfectly constructive interference? And then what is the intensity of the resulting wave for these waves interfering perfectly constructively? Okay, so remember that the intensity is proportional to the amplitude squared. So you have to think about what happens to the amplitude when these waves interfere constructively, and then how does that relate to the intensity of these waves that have now interacted constructively?